In the previous video, we looked at finding the test statistic and the p-value for a significance test, essentially putting our null and alternative hypotheses to the test. And now let's return back to our conclusion. So just to recap what we've been so far is, in this example, the claim was that the mean systolic blood pressure of men in an age group is 130. Now, when we're looking at our specific sample to test our particular group, we got a value of 128. And our alternative hypothesis is that, well, is our data different from the mean or not? Now, we went through and calculated the test statistic and got negative 1.09 and figured out the associated p-value with this alternative hypothesis, which we came to a conclusion of about 27 to 28% of the time. And basically, trying to summarize what this number means is about 27 to 28% of the time, we would get a value of our sample that is this far off from the actual value, like 27, 28% of the time, fairly frequently. So what this means is that there's a pretty good chance, about 1 out of 4, that we would get this sort of answer even if the actual mean of our group was 130. So remember that this is not very strong evidence, because random chance would have us get this sort of data fairly frequently. So basically, we cannot come to the conclusion that our age group, that this particular group of executives is different from the average, because it's not that different. Now, maybe if we would have gotten a score if we would have gotten a sample mean like 120 or 140, that might be significant, and that would always have a lower associated p-value. And things you can remember about p-values is that lower means stronger significance. Higher p-values are worse because random chance means it would happen more frequently, and we can't sort of rule it out. Because again, kind of the key here is that if it's very, very unlikely to occur, it's probably not just due to random chance. If it is fairly likely to occur, how can we rule out random chance explaining these differences in the data? And we can't. Because 1 times out of 4, we would get this bad of a result. So kind of returning to the logic is, there's always 2 conclusions we're going to make in a test. We're either going to reject the null or fail to reject the null. We never confirm the answer, but here what we'd expect is that there is not a significant difference because we have such a high p-value. But essentially, remember, it all comes down to what's our significance level, alpha. And in this particular example, we have we weren't told alpha value. We weren't given a significance level. But as I said in class, it's usually like 0.1, 0.05, 0.01, something like that. And those are kind of common levels of alpha that we see in the real practice. But basically, remember that if your p-value is less than alpha, this means that you reject the null hypothesis. And if your p-value is greater than or equal to alpha, or let's just say greater than, because it's rarely going to be exactly equal to it. But if you get a value that's higher than alpha, it means we fail to reject the null hypothesis. And there's always 2 cases we could have, right? So we come up with a p-value. Let's just say I did not give you a significance level here, but remember, it's not like a final answer. It's sort of like it's a range of values. It's kind of like a correlation value where it gives, and it's a numerical representation of an answer. So let's just say 10% is our significance level. Here our p-value is greater than alpha. It's greater than any typical significance value. And when our p-value is greater than alpha, we fail to reject the null hypothesis. And again, there's only 2 conclusions you can make. When p is greater than alpha, we fail to reject the null. When p is less than alpha, we reject the null. And all this means is we cannot conclude that our blood pressures are significantly different from the actual claim mean of 130. And that's kind of what I was thinking to begin with, because it's not significantly different. But again, we need to run through the math and kind of determine what's the probability of these things happening. And now the other thing we shouldn't conclude that our executives have the same systolic blood pressure as the general average, because logically speaking, we have not proven anything. There's still only a 28% chance that it will be this different, but it's not a significant difference. And that's kind of the key with the significance test. We want to determine how significant is our data. And if it doesn't meet the level of significance, we can't kind of move on per se and finalize a conclusion.